we should all be at the beach. I put this up here for a few reasons. One, so you have something to read while Ethan was introducing me, but also because it captures what is sort of increasingly becoming my motto. I direct an institute in Arizona called the Origins Institute, which is about origins. And really, if I try and think about the forefront of science, or almost all of human inquiry, this idea of how we got to where we got to in the first place is really the big question. And I want to talk about that in the present context in a much grander way, and talk about how we got to where we got to, namely how the universe got here. And I want to talk about the fact of how much not that we know, but rather how much we don't know. Since one of the great things about the Center for Inquiry is that it's about thinking, which is increasingly rare, and it's about the fact that there are mysteries, and not knowing everything can be actually very interesting. In fact, it's probably more interesting than knowing everything, because as we know for people who are religious, when you know everything, you usually don't know much. But so anyway, what I want to do is in fact talk about a mystery story, so I'll show you, and we'll begin the mystery story in a second. I want to just first focus on these things here. Last night, I went out with my friend Nancy, and we walked out. I wanted to look up in the sky to see these things, but it was raining on us. And so some of you may not have seen them before if you live in Vancouver. They're called stars. And the universe is full of them. And it's a beautiful night in the country. You will look out and see these things, and it's spectacular. But as spectacular it is, what really is interesting, and I hope we can see that maybe the contrast might be better for where you are than I am for some of these slides. But the most amazing thing about the universe is the stars, as beautiful as they are really the tip of a cosmic iceberg. The really important stuff is the stuff between the stars, the stuff you can't see. And that not only is relevant for our past, but will determine our future. And, oh, well, I don't want that far down. I guess, well, let's see how it goes. I'd rather not allow people to sleep if you put it down too much. Okay, let's see. If there's a slide that people really want to see, I can turn it down. Anyway, okay, so I want to talk about the stuff between the stars, and I do want to begin this as a mystery story, so let's begin. It was a dark and stormy night, and it was 1916, and Albert Einstein had just developed his greatest theory, the theory of general relativity, the first theory of not just how objects move through space, but it was the first theory of space itself, a theory that told us that space was dynamical. It could respond to the presence of matter and energy by expanding, by contracting. And it was a remarkable theory, a beautiful theory, a theory that was clearly right, except it suffered from a problem. It didn't describe the universe in which we lived. Nowadays, that doesn't bother physicists too much, but it used to. And Einstein was bothered by that, because, see, the problem with that theory was, in 1916, when you looked out at the stars, as you do now, you looked out, the universe appeared to be static and eternal. The stars were not moving, the universe was out there, sitting out there, and it appeared to be been that way forever. And the problem with general relativity is that it suffered from the same problem that Newtonian gravity suffers from, namely, gravity sucks. Okay, it always pulls, it never pushes. Any undergraduate student knows that. And the problem is you can't put stars out there and just have them sit there, because gravity is universally attractive, and the universe would collapse. And that's the problem. And so, but Einstein figured out a solution to the problem, but I want to show you how he did it. So, I'm going to show you Einstein's equations. And I've asked for the doors to be locked on either side now. And, so, this is for my friends who are here who are doctors. Hopefully they'll understand this. Okay. The left-hand side equals the right-hand side, so we're all okay with that. Okay. Now, it's not completely facetious, because in Einstein's equations, the left-hand side represents the geometry of space, the curvature of the universe, all the stuff that relates to how space responds to matter. And the right-hand side is the source of that curvature, which is the energy momentum of the universe, of all the stuff in the universe. And I'm a theoretical physicist, so I have to show you the actual equation with the indices there. That's much more illuminating. Now, as I say, that was Einstein's equations. It suffered from this problem that everything would collapse, just like Newton's law. But Einstein Einstein realized he could solve the problem by adding an extra term to the left-hand side of the equations. And he called that the cosmological term. This was a term, if you added it to the left-hand side of the equation, what it would produce would be a small repulsive force throughout all of empty space. Okay. So small you'd never see it here on Earth. You'd never measure it, wouldn't screw out the motion of the planets around the sun. It would be irrelevant on scales that humans live on. But it could build up over the scale of the universe so it could hold apart distant stars and galaxies and balance them against their universal attraction. So he thought that this could result in the static universe that we lived in. And that was fine. The problem is that almost immediately after writing it down, problems arose. There were mathematical problems, but the real big problem, in fact, was that the universe wasn't static. In fact, within a few years of writing this down, people began to realize the universe wasn't static. And a few years ago, I was on leave in Switzerland, and I got a hold of this postcard from Albert Einstein to Hermann Weyl, who was a very famous mathematical physicist. And some of your German is better than mine, but this basically says here, so 1923, he said, if you get rid of a quasi-static universe, then out with the cosmological constant. What he realized was, if the universe wasn't static, you didn't need this damn cosmological constant. Say damn in this room, actually, it's great. Anyway, you didn't need it because, in fact, you didn't need any repulsive force. Because if the universe were expanding, gravity made the universe attractive and just worked to slow down the expansion. And the big question became, and it became the big question of 20th century cosmology, the big question of physics is, well, if the universe can slow down, is there enough stuff in the universe to stop that expansion of the universe and cause it to collapse into the reverse of Big Bang, Big Crunch? Whatever, would the universe end with a bang, Big Crunch, or a whimper? Would the universe expand forever and the stars die out? And that became the central question of 20th century cosmology. And in fact, it was that question which got me into the field, in fact. As a particle physicist, I was interested in issues that I thought could help resolve that question. I wanted to be the first person to know how the universe would end. Seemed like a good idea. And so I got involved, and you'll see what happened eventually. But, now, this was in 1923, but the first person to actually convince the world that the universe was expanding was a little bit later, was this guy here, one of my heroes, Edwin Hubble. He's a hero because he gives me faith in humanity, and I really need it now at the present time, especially in the United States. But this guy, Hubble, he began life as a lawyer and then became an astronomer. So that there's hope. And he was indeed made many great discoveries. The one I want to concentrate on, I'll talk to you about in a second, but since we've got all night anyway, I'll tell you about the first one, which should put things in perspective, I think. In 1925, with the Mount Wilson telescope, he used the first large telescope to resolve a problem, a big controversy that had existed. It's amazing to think that in 1925, our universe was the Milky Way galaxy. That was it. That was all people knew about. One galaxy, the galaxy we lived in. And when you looked through telescopes that were available up to that time, when you looked out, you saw these fuzzy things. And people debated what they were. They were called nebulae, which is Greek for fuzzy thing. And there was a big debate about what they were, and then people thought, well, they could be this or that. And then with the Mount Wilson telescope, what Hubble did was, in fact, show us that they were actually not just in our galaxy, but in fact they were other island universes, other galaxies. They were outside of our galaxy, they represented other galaxies. And we now know in the observable universe that there are 400 billion galaxies. And until literally a lifetime ago, a human being who was alive then could be alive now. And at that point we knew of one, now we know there are 400 billion. So our picture of the universe has changed about as much as it could possibly change in a single human lifetime. It's continuing to change. It's an exciting time because we're learning things, new things, some of them are wrong, some of them will be wrong, that are changing our picture of everything. So it's very exciting. Because if you're a theoretical physicist, there's nothing more exciting than being confused. And I'll show you that we're very excited. Okay, so what did Hubble tell us? Well, Hubble, when he looked out at these are not sperm, these are galaxies. When you look from our galaxy, look at others, they're all moving away from us. And if you look at galaxies that they're moving a certain velocity, galaxies that are twice as far away are moving twice as fast. Galaxies that are 3 times as far away are moving 3 times as fast, and so on. And so, what does this tell you? Okay, well, it tells you obviously that we're the center of the What it really means is that the universe is expanding. And it's hard to see why this should tell us that the universe is expanding. And so I've done a lot of different ways to try and demonstrate this, but I think this works. See, the problem is we're myopic. That's actually a big problem that science is designed to solve. We look at the universe and we think the universe is supposed to be like it is here, and that everything is supposed to be the way we're used to. As societies, we tend to do that too. That's the big problem, because we've got to learn that the universe is the way it is, whether we like it or not, which would be the greatest gift we could give to humanity if we just convince people of that simple fact. But also that it doesn't have to be the way we're used to it being. And so we got to get out of our myopia, and that's, to me, the greatest gift that science can give humanity, is it can force us out of our petty picture to understand the universe from a different perspective. And so to understand the universe from this perspective, I want to get outside the universe. And that means getting outside the box. So the problem is we're stuck in our universe. So to see what's happening, I made another universe, one that's easier to see from the outside, a two-dimensional universe, with galaxies located at regular intervals. So these are all galaxies. And this is the universe at time t1. This is the universe at time t2. And you can look and see that this universe is bigger than that one. It's just, the galaxies have been expanding apart. So if you're outside the universe, it's very easy to see that it's expanding. But what would you see if you were in that universe? Well, just pick a galaxy, any galaxy. So pick that one. To see what you see from that one, I want to superimpose this image on top of this image, putting that galaxy on top of where it was, and you will see that, in fact, what you see is exactly what Hubble saw. Everything is moving away from you, and those things that are twice as far away have moved twice the distance at the same time. Those that are 3 times as far away have moved 3 times the distance, etc. And it doesn't matter what galaxy you're on. Pick any galaxy and do the same thing, and you see exactly the same thing. So, either no place is the center of the universe, or every place is the center of the universe. You decide which one you like better. It doesn't really matter. That's philosophy, and therefore it's important. Anyway, the point is that the universe is expanding. And that's profoundly important, because it changes everything. And as indeed it implies that we didn't need the cosmological constant of Einstein, it applied a very profoundly different past and an importantly different future. In fact, it provided a past that was somewhat controversial, because suddenly the universe had a beginning. And that had theological implications, as you might imagine. And in fact, the Pope at the time, another aside that I haven't had to talk about, what the heck, Pope Pius actually gave an encyclical right after this was discovered, that in fact that science had proved Genesis. Actually, it was the creation. In fact, however, rather interestingly enough, the first person to really show that there had to be a Big Bang, the first physicist, the theoretical physicist, was a Belgian priest named Georges Lemaitre. So he's a priest, but also a physicist, and when the Pope said that, actually Lemaitre wrote to the Pope and said, "Stop saying that." Right? Because this is a scientific theory. It can be tested, it can be falsified. You can take it if your religious inclinations point you in that direction to say that somehow it validates creation. On the other hand, you can take it to be that the laws of physics, as we know them, take us back to t = 0, and you don't need any God. Okay? However you take this depends upon your philosophical or religious background. But whatever you believe, there was a Big Bang. It really happened, and you have to interpret it. Okay, so it really did change everything. Now, in fact, let's see. I want to talk about how this is such an important result. I want to talk to you about how we know it, because it's going to come back and impact on our understanding of the universe at present. So Hubble measured the fact that galaxies are moving away from us, and their speed is proportional to the distance. So to measure that, you have to measure speed and distance. Okay? So those are the two observables. So how do you measure the speed of galaxies? That turns out to be the easy thing. These cowboys know how. Okay, they're on a plane, they're looking at the train, and one cowboy says to the other, "I love hearing that lonesome wail of the train whistle as the magnitude and frequency of the wave changes through the Doppler effect."